And if you like what you see on the dome today, come up and see me at the control booth behind you, and I'll tell you how you can get this software. It's a free download, so it's supported by NASA, and you can install this software on your own computer at home if you've got the right kind of computer, and you can have some fun. Try what we do today. Now, what we're doing is we're going to leave Earth behind, and we're going to travel out of the solar system to the edge of the galaxy and beyond, to the edge of the observable universe and back by 5 o'clock. I'll be describing what we see to you, and during the presentation, as always with all of our shows, we would appreciate it very much if you could please refrain from eating, drinking, snacking, or any kind of photography or recording. We'd also, this would also be a great time to silence your personal electronics and to tuck away or turn off any light-emitting devices like cameras, cell phones, tablets, anything that gives off light that can distract the people around you in the dark or even wash out the image on the dome overhead. At the end of the show, we ask that everybody exit out through the doors at the top of the stairway, either stairway, but at the top. If getting up these stairs is going to be a problem for any of you, just stay in your seat at the end, and our staff will assist you out the lower exits if that's more convenient. But everyone else, please use the doors up here at the top. So with that, are you ready for a trip into outer space? Yeah, you can do better than that. All right. Okay, so what we're going to do is transport ourselves first, not into outer space completely, but we're going to turn down the lights and have a look at one place where NASA is currently trying to launch a rocket into space. This is pad 39B at Cape Canaveral in Florida. We are 1 kilometer above the pad, so this is where the rocket stands. And as we travel higher and higher up, you'll get to see more of this area around Cape Canaveral. You know, one famous astronomer once said, outer space is not that far away if cars could go straight up. It's only an hour's drive. And that's true because the officially recognized boundary of outer space is only 100 kilometers up, or about 62 miles. We're stopping right here, which is 7 kilometers up, because in addition to pad 39B, here's pad 39A. Now, B is where NASA's trying to launch the Artemis 1 mission from, and pad 39A is where SpaceX usually launches its rockets from. You can see the long road to the vehicle assembly building here, and over on the lower left, this is the big long runway that was used by the space shuttle, which ended its service in 2011, but the runway is still there. And now we're up about halfway to space, about 40 kilometers up. And as we go higher and higher, the air gets thinner and thinner. So what happens if you get all the way up to 100 kilometers, which is where we are right now? This is the edge of space as recognized by international aeronautical organizations. Up here, the air is so thin that things like wings, control surfaces, rudders, flaps don't work because the air is just too thin to allow that. So to maneuver around, you have to use rockets. That is what defines outer space. Now, people argue a lot about what number it is. It's 100 kilometers or 62 miles, or maybe it's 50 miles, or maybe it's something else. And there are lots of arguments about that, and if you go up that high, does that make you an astronaut or not? Well, actually, it's more of a functional definition. It's where air control surfaces don't work. So that's what outer space is. We passed 100 kilometers, and we're going to keep going a little bit higher. We're going to go up to about 400 kilometers, which is the altitude at which the International Space Station orbits our planet. So this right here is the view that the astronauts on board the International Space Station have as they zip around our planet, going about 17,000 miles an hour, circling Earth every 90 minutes. So it's a beautiful, magnificent view that they have of our planet. And this is currently as far as humans travel from the Earth. But right now, we're going to go a little farther than that. We're actually going to go beyond to the distance that humans traveled about 50 years ago. As we do, we'll break away from Earth, leave our planet far behind. You can see our beautiful planet there. And we're going to go as far out as the moon. So about 1,000 times farther than the orbit of the space station. That's 400 kilometers or 250 miles. We're going to go out about 250,000 miles out into space. And that's as far as our moon is. It orbits our planet at a distance of about 250,000 miles. Now what we're going to do is we're going to have to search around for the moon. And to do that, I don't want to move things around too quickly, not fly around too wildly, because this is entirely live. But I'm going to try not to fly into any black holes or crash into any stars. But I want to be careful about our motions here. I see the moon, so I'm going to focus on the moon. I will turn just a little bit and go back in to have a look at our nearest neighbor in outer space, our own satellite, the moon. Now the moon is, again, about 250,000 miles away from Earth, about 240,000 miles, and it is a dry, rocky object about 2,000 miles across. It has no air, no water, no atmosphere. It's covered by thousands and thousands of craters. And also it has these dark patches that you can see called maria. That's a Latin word which means seas, because early astronomers thought that those dark patches were bodies of water. So they called them seas and oceans. And they gave them beautiful names like the Sea of Serenity, the Sea of Tranquility, and the Sea of Fertility, the Sea of Rains, and names like that. But the other lighter colored areas that have a lot of craters on them, those are called the highlands. And you can see the craters are just side by side and on top of each other. Those craters were formed by the impacts of asteroids and comets during the moon's past. And then more recently, large impacts fractured the crust of the moon, caused lava to bubble up and spread out. It dried, cooled, hardened into those dark maria that we see. So that's why the moon looks the way it does. Here's a beautiful, right in the center of our field of view, there's a beautiful range of mountains on the edge of the Sea of Rains. This range of mountains is called the Lunar Apennines. Beautiful range, and there are so many features that have been given lovely names on the surface of the moon. That's as far as humans have traveled, 250,000 miles, and one day NASA and other space agencies hope to send people back to the moon. NASA's got a program called Project Artemis, which is trying to lift off, and has plans to travel to the moon and land people there in about 2 years or so. That's the plan. And other countries have similar plans as well. But we're going to travel even farther out than that. And to see how far we're going, just in comparison to the various objects that we're visiting, we're going to add in the trails of the planets, the orbit lines that we see right here. So there's the Earth's orbit around the Sun and the Moon's orbit around the Earth, which we can see right now in the center of our field of view. And as we back away, we'll see the orbits of the other planets around our star, the Sun. So as we back away, we see the Sun appearing over on the right, the star at the center of our solar system, and we have a few planets orbiting around it. The nearest planet to the Sun, of course, is Mercury. Then comes Venus, and then we on Earth are the third planet from the Sun. Here's Mars, the fourth planet out. And after Mars, there's a big gap, which is filled with chunks of rubble, debris, rock, and these are called the asteroids. These are leftover material from the formation of the solar system about 4.5 billion years ago. But beyond the asteroid belt, there are other planets. We have not just the 4 small inner planets, but some really big ones like Jupiter, Saturn, Uranus, and Neptune. Those are the orbits way out there. And these planets are so far out that the light of the Sun takes about 4 hours to get all the way out to the orbit of Neptune. That's how far away some of those outer planets are. Now, when astronomers talk about how far away things are in space, They don't really talk in terms of miles so much, because trying to use miles to measure things out in space is kind of like trying to measure the length of Golden Gate Park in inches or millimeters. The numbers just get way too big. So they use a scale that's based on the speed of light. At the speed of light, which is 186,000 miles per second, at that speed you could travel 7 times around the world, around Earth, in 1 second. You could travel from the Earth to the Moon in about 1.5 seconds. You could travel from Earth to the Sun in 8 minutes. So that distance right there takes 8 minutes for light to travel. But then it takes about 4 hours for light from the Sun to get all the way out to the orbit of Neptune. So the astronomers talk in terms of light minutes, light seconds, light hours, and as we get farther out from the Sun, we're going to start talking about things in terms of light years. But before we do that, let's see how far some of the most distant spacecraft have traveled from our planet. About 45 years ago, we started sending spacecraft out in the form of Pioneers 10, 11, Voyager 1, Voyager 2, and then New Horizons. Here's the track of Pioneer 10, which was launched way back in 1973, going off all by itself to the right. And the other trails here are the other spacecraft that followed it, Pioneer 11, Voyager 1, Voyager 2, and New Horizons, which recently passed Pluto. The farthest one is Voyager 1, way out here, all the top path, which goes way out. And that has been in space now for about 45 years. And it's about 14 billion miles from the Sun, a distance that takes light about 21 hours to traverse. So as long as Voyager 1 has been in space, our most distant spacecraft, it hasn't traveled as far as light can travel in 1 day. It's only traveled about 16 or 17 or 21 light hours into space. So that's how big the universe is. I mean, we haven't really left our solar system because there's a lot of other stuff out here too. In addition to these planet trail or these spacecraft tracks, I also want to show you another belt of objects, which is kind of like the asteroid belt, but only out around the orbit of Neptune. This is a region called the Kuiper belt, and it's filled with lots of asteroids, dwarf planets, and comets, and there's a lot of them out here. And this area is kind of messy. There's a lot of stuff out here, including objects that forced astronomers to reclassify what used to be called a planet, the object known as Pluto, which was discovered in 1930, but in 2006 it was reclassified as a dwarf planet because there's so many other objects out here which are kind of like it in the same neighborhood. So there are 5 dwarf planets in our solar system, as well as all this other stuff that you see in the Kuiper belt. And that is just some of the stuff that is in our solar system. So let's travel farther out now. We'll leave the Kuiper belt behind, and we will continue traveling farther out from the Sun. As we do, let's let the Sun be assume the normal relative brightness as it would compared to the other stars. And now as we enter interstellar space, we'll pass by some of the stars that we see in the sky, and we get a sense of the depth of the universe now, how far out things really are. So now we're talking about things that are light years away from the Sun or from Earth. But as we travel farther and farther out, we're going to pass one more sort of a boundary, which is the extent of our human influence in space. This is as far as any artifact of humanity has traveled, and it is our radio signals. Our radio signals have been traveling outward from Earth for about 90 years, forming a large radio bubble, which is about this big, 90 light years in radius, or about 180 light years in diameter. And this is as far as our radio signals have traveled into space. Now, this is so far out, can you even see the Sun anymore? It's not easy. It's somewhere there in the middle. But you can see that this radiosphere encompasses some nearby stars. There are a lot more that are way outside. But if there were some civilizations within the radiosphere, if civilizations living on planets orbiting some of the stars that are inside the radiosphere, they may have picked up our radio signals, and maybe they're listening. But if they're outside, if they orbit stars that are outside the radiosphere, they don't know about us. They haven't received our radio signals yet. Interesting thing to think about. But this radiosphere is expanding 1 light year every year. But I'll leave it on right now because as we travel farther and farther away and see it recede into the distance, we're also going to see how big it is compared to the size of our own Milky Way Galaxy. I'm going to change our angle just a little bit as we travel farther and farther out. About 100 years ago, astronomers thought there was only one galaxy in the entire universe. And then an astronomer named Edwin Hubble said, no, that's not right. There are other galaxies out there. And some of them are pretty big. A lot of them are really far away. And there are lots and lots of them. Some are getting even farther away still because the universe is expanding. Galaxies are moving apart from each other. This is our own Milky Way Galaxy, a huge disk of several 100 billion stars that measures about 100,000 light years across. So it takes a beam of light 100,000 years to go from one edge of the galaxy all the way across to the other, even traveling 186,000 miles per second. But the Milky Way Galaxy is a very flat structure. Remember, I said it's a disk. So it is very flat. If we travel down through the plane of the galaxy, you can see how thin it is. And yet it's so wide, so broad. That's our own galaxy. It's a typical barred spiral galaxy, and there are lots of other galaxies like it in the universe. In fact, as we travel farther and farther out, we'll see that our own Milky Way is just one member of a cluster of galaxies, a small cluster called the local group, which consists of about 80 or so galaxies, and we can see a few of them here. Farther beyond, there are other galaxies that we can see. Now that we've left the Milky Way, every spot of light you see on the dome overhead is not a star, but rather a galaxy. And this is all based on actual survey data, which shows us the relative positions of all the galaxies with respect to each other, not all of them, but many galaxies with respect to each other. And there are many, many, many galaxies out there that we can see. Now, the galaxies are clustered together into large groups, clusters of galaxies, or superclusters, which can contain thousands of galaxies. And as we travel farther out and get a broader view, we see that there's some structure to the way galaxies are distributed in space. They are clumped together in some cases, forming large groups. They are separated by voids or big empty spaces. They form filaments or sort of a spongy structure out there. All of this made of galaxies. All of this. Now, one thing you might notice about this three-dimensional model of the universe, an actual map based on real data, one thing you might notice about this is that it makes the structure of the universe look rather interesting. The universe looks like a big butterfly, doesn't it? Or like an hourglass. Is this the real shape of the universe? Well, no, it's not, because this area here, the narrow section of this hourglass, is not empty space. It's just a part of the universe that we haven't mapped very well yet because there's something blocking our view. What's blocking our view? It's our own galaxy. Remember, the Milky Way is a disk of several 100 billion stars. Well, the plane of the disk lies right along this gap here in the hourglass. And so all the dust and gas and stars in the Milky Way are blocking our view of what's out here. Gradually, as our technology and techniques get better, we will be able to fill out the map a little more uniformly, and the map will look a lot nicer. It will look less like an hourglass or a butterfly. But right now, this is the shape of our model of the universe. And if we travel even farther out, we'll see some of the most distant objects that have been observed by astronomers, things called quasars, which are represented by these orange dots that you see way over on the sides, way over to the left and right. Quasars are believed to be the very, very hot, energetic cores of young galaxies, newborn galaxies. They're on the average about 10 billion light years away from us. And to be as bright as they are from that tremendous distance, they've got to be super energetic. And that's what astronomers think is going on. They are powered by supermassive black holes at their centers. And those are the most distant single objects we have detected, quasars, or quasi-stellar radio sources. But there's more. Just beyond that, there is something else. Permeating the entire universe, coming from all directions, is a faint radiation, a microwave background radiation that comes from all directions, which is believed to be a remnant of the first light in the universe that was able to travel from one place to another. Now, I said earlier that Edwin Hubble showed that the universe is expanding. Galaxies are moving away from each other. Well, calculating backward, astronomers tried to figure out when that expansion began, and they think it began just under 14 billion years ago. Well, at that point, the universe was very hot, very dense, very opaque, and then suddenly, at a moment called the Big Bang, it became very transparent, very rarefied, and very cool. And this is the first light that was able to travel from one place to another through the universe as it gradually became more and more transparent. That faint cosmic microwave background is said to be the best evidence that astronomers have for the Big Bang, that it actually happened. So this is as far as we can see. This is the edge of the observable universe. Since this is as far out as we can travel, there's no place else to go but back in. And as we travel back the way we came, it might occur to you that it sure looks like we have put ourselves at the center of the entire universe. Is that really where we are? I know a few people who think they're the center of the universe, but we're really not. This is really just the result of the fact that we're the ones who made this model. We made the map, and everything is based on our perception of everything around us. So if there were somebody else in some other part of the universe, way over on the side here, their map of the universe would look very similar, with them at the center, because it's based on their point of view. But aside from that, the universe is one mind-boggling thing after another. With all the galaxies we've seen, and all the clusters and superclusters and quasars and all this, what we're seeing really amounts to only about 5% of the total matter in the universe. Astronomers have very carefully observed the motions of the galaxies. And they've determined that what makes the galaxies move the way they do is influenced by the gravity of something else. There's more mass out there than we can account for just by seeing what we see with our eyes. Something else very massive is out there making the galaxies move the way we see them moving. This is something called dark matter and dark energy, and they are total mysteries to astronomers. They don't know what that material is, but that makes up most of the universe, about 95% of the universe. And what we see through our telescopes is really only about 4 or 5%. Traveling back in toward our Milky Way, we'll travel out to one of the outer arms, about 2/3 of the way out from the center. We see our marker, which is humanity's footprint, the radiosphere, telling us where we are in the Milky Way Galaxy. You might wonder if with all the stars that we've seen, all the galaxies, are there planets out there? I did mention that, kind of tease the idea earlier. Are there other planets in the universe? Well, according to astronomers, there sure are. And this is a map of some of the extrasolar planets that we have found. These are all the locations of stars that are orbited by at least one planet. We've been discovering these since 1994, and since that time, the current count stands at more than 5,000 other planets. So of all those planets out there, if those more than 5,000 planets, are any of them like the Earth? Well, we know that a lot of them aren't. We know that many of them are big, like Jupiter, and very close to their stars, things that are called hot Jupiters. Others are very small, others are very far from their stars and very cold, so they're not the right temperature. You need the right combination of things for a planet to be able to support life like Earth does. It's got to be the right kind of planet. It's got to orbit the right kind of star that doesn't give off dangerous radiation. It's got to be the right distance from its star, so it's neither too hot nor too cold. It's got to have the right components that can provide the nutrients that any life that evolves on it needs to survive. So there are lots and lots of things that a planet needs to have in the right combination in order to have an environment that supports life. And so far, we've seen some very interesting planets which might have one thing, might have another, but doesn't have everything. In all the universe, as far as we've seen so far, there's no place like home, like our planet Earth. A very fragile, very delicate place where life exists in a very delicate balance with its environment, one that we need to take really good care of so that our planet can continue to support the life that arises on its surface. And so with that, welcome home. Welcome back home to the planet Earth, and we hope you've enjoyed this tour of the universe. Thank you very much.